Hello everyone, welcome back to the another class of fundamentals of particle and fluid solid processing. We will continue our discussion on filtration and specifically on cake filtration. Last time we have seen the relation of the pressure drop with the filtrate volume without the filter medium resistance as well as including the filter medium resistance. So this two slides, the initial two slides basically summarizes that what we had concluded last time, that when the filter medium resistance is incorporated in the total resistance, then how the relationship between the pressure drop and the filtrate volume was derived. So here we saw that the total pressure was the pressure drop across the medium plus pressure drop across the cake. Now pressure drop across the cake we have explicitly seen earlier. Now pressure drop across the medium, which also contributes to the overall resistance, this one we assume that, say, this is also giving a resistance that has a equivalent packed bed depth of Hm with a resistance Rm, and then the total resistance was written in this form. Now again, this medium resistance that we have assumed as of a packed bed resistance of a certain height or thickness, we have considered that, or we have assumed that this thickness, okay, is basically, or the resistance is basically resulting from an equivalent thickness of cake resistance, which is Heq. So Heq, this much of cake, the amount of resistance is provides, we have assumed that that is the medium resistance, and then what we have done is that means this Rm multiplied by Hm, which is the specific resistance due to the medium multiplied by the thickness of the filter medium, is equals to the specific resistance for the cake multiplied by its equivalent height. Fine. And then we have also seen the amount of this cake, okay, amount of particle that is deposited. From there we had a relation of Heq, or the H equivalent. Now this Veq and Heq is the relation is that this Veq is basically the volume of filtrate that must pass through the filter media to form a cake height of H equivalent, and this property solely depends on the suspension and filter media properties. By doing so, we have come up with the expression for pressure drop including the overall resistance that consists of medium resistance as well as the cake resistance, and we have also found that what is the filtration rate. Now for a constant pressure drop scenario, which is frequently occurring scenario or most popular scenario, there if we integrate this expression, this filtration rate expression, we can have a relation of the time required to have a certain volume of filtrate, which is V. This expression is related with the specific cake resistance, fluid viscosity, so Rc, fluid viscosity, filter cross sectional area A, the pressure drop across the upstream surface of cake and the downstream surface of filter media. Then we have the V equivalent, which we mentioned that this is the volume of filtrate that must pass through to form a cake height of Heq, and V is the filtrate volume. So this is the relation that we derived and we have seen in the last class. Now the point is that once we have this cake deposited or the cake formed, this is say the cake layer. Now this we have mentioned that these are the solid particles is of more valuable to us or is of more importance than the fluid phase or the liquid phase. So then once we collect this cake, if we try to recover the solid particles, the liquids that are there in the pores of these solids, this has to be removed. That means the liquid staying within or with the solids, that has to be dried, washed, and we have to get back the solid particles. Now to have that, the washing phenomena or the washing process is typically done, which is called the cake washing. The purpose of this is to remove the filtrate from the particle pores, and this again I repeat that this is important when we try to recover the valuable solid particles that actually forms the cake. Now this removal of filtrate from the particle pores by washing, this it has been observed that happens in two processes. One process is that most of the filtrate, when the wash liquid is passed through that in a backward directions or in opposite directions where the filtration was happening, then most of this liquid that was staying with the solid particles actually goes away by displacement method. This wash liquid displaces those filtrate, okay, or those filtrate that are staying within the pores of the solid particles. By displacement technique, it actually displaces those liquids, and the volume equivalent to the or equals to the pore volume, that much amount can be removed by displacement only. But the rest of the part which are still staying in the interstices or less accessible areas or the less accessible regions, by diffusion into the wash solution, those filtrate are then removed. So after a certain point, the removal happens by diffusion only, but most of the fluid, most of the filtrate actually is removed by the displacement method, and this schematic shows this removal process, that here this is the volume of wash solution that is required, and this is the fraction filtrate in existing wash solution. Typically it starts with 100% initially, and then that decreases to a certain value. Once such plateau is reached, we consider the cake has been washed thoroughly, and then the drying or the evaporations or certain things can be done to recover the solid. So after filtration or completion of the filtration process, this cake washing phenomena happens to recover the solid particles. Now we will see, or we will solve a couple of problems that will help us to understand this theory part or the expressions that we have derived or we have seen how these are applicable. So let's start with this problem. The problem says that a filter has an area of 0.5 meter square and operates at a constant pressure drop of 500 kilopascal. The following test results were obtained for a slurry in water which formed filter cake that assumed to be incompressible in nature. So this is the data set that has been gathered, which says the volume of filtrate collected and respective time. The question is what is the time required to collect 0.8 meter cube of filtrate at a constant pressure drop of 700 kilopascal. This is the first part. The second part is that what is the or how much time it would require to wash the resulting cake with 0.3 meter cube of water at a pressure drop of 400 kilopascal. So these are the two parts that we have to solve. So let's concentrate on the first part. So that means here the filter area or the cross sectional area is mentioned, the operating pressure is mentioned, and it has been mentioned that let's assume the cake to be incompressible in nature. So that means voidage is constant, and then we have the filtrate volume versus time data. So what do we do with this data or the data set? Because the question is, what is the time required to collect 0.8 meter cube of filtrate at a constant pressure drop of 700 kilopascal? So which means we have to look at the expression of T by V that we have seen earlier. So say, how do we proceed this? Now this is the relation that we have seen, and in fact we have derived. Okay, so here RC is the specific cake resistance, fine. Phi, we know the value, HA by V. So basically all these parameters we have to find out, or we have to know to find out the value of T to filter a certain amount of V. So which means if we have the right hand side solved, then we can calculate this V, what is the time required for filtration of this much amount, this V amount of the filtrate. Now looking at this expression, you can easily find out that T by V, this complete parameter, is a constant portion multiplied by V plus another constant term. That means it is in the form of Y is equals to mx plus C, because the cake is incompressible. So RC is constant, fluid properties are not changing, cross sectional area del P, these are the value that are given already, which means we have to find out this VQ and RC mu phi, these terms, since these are not explicitly mentioned. So you can think of that we have to find out these two terms, basically that RC mu phi, which is common in both the parameters. Okay, so this is one unknown, this is the second unknown term. If you find out these two, then you can find out that what is the T for a particular V, because A and del P, these two information are given. Now you have T versus V curve. Now this, as I mentioned, represents Y is equals to mxc, where Y is T by V and X is V. So if you convert the given set of data to V and T by V, because volume is mentioned and S is mentioned T, so basically we find what is T by V, and then if we plot this T by V, again this is the schematic, not to the scale. The point here is that if we have all these points and this y is equals to mx plus c. Okay. So, which means the gradient would give us this parameter m, and the intercept, which is this one, the c component. So, from this graph we can easily find out what is m and what is the intercept. The calculation shows, or if you do the calculation, you would see this intercept will cross say around 1000 second per meter cube, this value, and the m, the gradient would be 4000 second per meter to the power 6, which means now you have these two expression or these two equation to find out these two components that I mentioned. If I say this is 1 and VQ as 2, you have two equation and two unknown, which means you can now solve and find out what is RC mu phi and VEQ from these two expression. If you do that, for A is 0.5 meter square and del P is 500 kilopascal, because these are the parameters that are given here, that the filter has an area of 500 meter square and pressure drop 500, this is 0.5 meter square and 500 kilopascal. So, if we take those values, we find these two parameter. These are the numerical value. Now, if we replace this 1 and 2 in this previous expression, which is this T by V expression, we find a relation, that is T by V is equals to 0.5 multiplied by 10 to the power 9 divided by minus del P, this whole thing multiplied by 4V plus 1. So, this is the T and V relation with del P. Now, for a constant pressure scenario, because the question is asked, again we go back to the question. The question is says the time needed to collect 0.8 meter cube filtrate at a constant pressure drop of, which is the constant pressure drop of 700 kilopascal. So, that means now it is a constant pressure drop filtration process, and in that case we replace this del P as 700 or minus del P as 700 kilopascal, 700 multiplied by 10 to the power 3 pascal, and the V, the filtered volume required is 0.8 meter cube. We replace this numerical value in this expression and we find out that the time required is 2400 seconds, which is 40 minutes. I hope this process is clear. Now, if we go to the second part, that is the time required to wash the resulting cake with 0.3 meter cube of water at a pressure drop of 400 kilopascal. Now, at this point you have to understand that this washing of cake will happen at the end of the filtration process. Once the filtration process is completed, at that point this washing will take place in a reverse direction, reverse flow direction. Okay. So, now that means if we now look at the second part, how do we solve? We know this is the filtration rate expression. So, this filtration rate expression, and at the end of the filtration experiment, what is the filtration rate? At the end of a filtration rate with this 700 kilopascal pressure drop and 0.8 meter cube of volumetric flow rate that we have required, we find that filtration rate is basically 1.89 multiplied by 10 to the power minus 4 meter cube per second, because in this filtration rate expression all the right hand side parameters are known, because del P is 700 kilopascal, area is known to us, that is 0.5 meter square, RC, mu, phi, these values are known. So, which means that this filtration rate at the end of these expressions, and we have also found out what is VEQ, which is 0.125. These two parameters are replaced here. So, on the right hand side we basically know everything, including the A in the left hand side. So, we find out what is dV by dt. Now, we assume that this washing liquid or the wash water that will now flow in the reverse direction to wash this cake will have the similar or the same physical properties as of the filtrate, because that is not explicitly mentioned in the problem. So, we assume that it would have the same physical property as of the filtrate. The washed liquid will have the same physical properties. So, that means during wash period, if the pressure drop is 700 kilopascal, the wash rate is the same of filtration rate, because that is the point where we stop the experiment, and then this washing is happening. So, if we had maintained this 700 kilopascal of pressure drop across the bed, then we would have achieved this much of filtration rate. But in the second question it is asked that what would be the filtration how much time it would take to process with 0.3 meter cube of water at a pressure drop of 400 kilopascal. It is not at 700 kilopascal. So, washing is happening at 400 kilopascal. Now, again if we refer to this expression, what we observe that this filtration rate, this we have also mentioned earlier, is proportional to this pressure drop, directly proportional. So, if we change the flow rate, or if we change now the pressure drop, it eventually lead to the directly proportionate change in the washing rate or the filtration rate, which is equal here. So, which means when we reduce the pressure drop to 400 kilopascal, the rate what was there during the 700 kilopascal pressure drop, this was the filtration rate that we have calculated, which is effectively the wash rate at 700 kilopascal. Now, since the pressure drop is reduced to 400 kilopascal, we have the reduced value of wash rate. So, now we have wash rate at 400 kilopascal, which is 1.08 multiplied by 10 to the power minus 4 meter cube per second. So, which means we are washing 1.08 multiplied by 10 to the power 4 meter cube of wash water okay, per second. So time required to pass this 0.3 meter cube of wash water at this rate would be 0.3 divided by 1.08 into 10 to the power 4 second, which is 2778 seconds. So I hope this process of solution is clear to you. That means if we quickly go through the another problem of similar style, let's see whether you can quickly solve this problem. So again, the other problem says that a filter area of 0.1 meter square operates at a constant pressure drop of 400 kilopascal. Then the following tests results were obtained for a slurry in water which formed cake filter cake, which can be regarded as incompressible. The V versus T data set is given similar to the previous problem. The question is time needed to collect 1.5 meter cube of filtrate at a constant pressure drop of 300 kilopascal on a similar filter with an area of 2 meter square. Not exactly the same filter, but a large scale version of this one, because here it was 0.1 meter square. The question has been asked for 2 meter square. So a large scale filter. What is the time required to process this much of filtrate? The rate of passage of filtrate at the end of this filtration, and time required to wash the resulting cake with 0.5 meter cube of water at a constant pressure drop of 200 kilopascal, which is exactly or similar to the previous problem that we have solved. Only the first part has a difference, that now the area has changed to 2 meter square from 0.1 meter square. So which means if we quickly look at the solution, the point is that V versus T by V data set is given. Okay. If we plot this, it would give us, this is the T by V axis in the y axis, and this is the V. The intercept value would be 10,300 and the gradient would be 2.09 into 10 to the power 5. From these two expression, we find out these two variable which I am marking as 1 and 2. It is not the variable, but the parameters. These values, once we calculate numerically, we find that for A of the area of 0.1 meter square and del P of 400 kilopascal, these values are these two values, which means our T by V expression is this one. Now the point is that the first part, the area has changed now. V is known, del P is known. So if we look at this expression once again, that T by V expression, here we have now calculated RC mu phi and VEQ. The area is now 2 meter square, del P 300 kilopascal and V is 1.5. We replace this in this expression, we get T as 2229 seconds. So since this is the similar type of filter and the filtrate is same, identical, the properties are identical. So that is why we can safely use these two variables or these two parameters values as it is in that expression, T by V expression. Once we do that, again similar to the last problem that we have solved, this filtration rate expression we can solve for all the known values on the right hand side. These are the values that we have calculated, and these are the values that are given. It gives the filtration rate as 3.4 into 10 to the power minus 4 meter cube per second. Again, assuming that this wash water is having the same physical properties as of the filtrate, we know now that for this much of pressure drop, this is 300 kilopascal, we have a wash rate of 3.4 into 10 to the power minus 4 meter cube per second. But currently the applied pressure is 200 kilopascal, which means our wash rate or the filtration rate will be reduced proportionately. And with this rate, to process 0.5 meter cube of wash water, the time required is again 0.5 divided by 2.27 into 10 to the power 4 seconds. Which is 2203 seconds. This is the final answer. So, this is the time required for washing of the cake with 0.5 meter cube of wash water and 200 kilopascal of pressure drop. This is the filtration rate at 300 kilopascal, and this 2 meter square of the area, and this is the time required for that filtration. I hope this solution methodology is clear to you. We have seen two similar type of problems, and I hope this theory of cake filtration, particularly for incompressible cake, is clear to you. In the next day, we will see the example of compressible cake and the filtration operation related some points. Till then, thank you for your attention.